let's explore a little bit some of the properties of linear transformations generally. So here we have a theorem that describes a couple of the simple properties that we have of linear transformations. So let's let T be a linear transformation that maps a vector space V to a vector space W. Okay. So again, V could be Rn, or it could be a subspace of Rn. Any vector space will do. Then we have two observations. First, that the transformation of the zero vector in V is equal to the zero vector in the codomain W. Okay. And second, T maps any line in the domain V to generally a line in W. There are a few special cases where it could map to a single point in W. But the most common situation is that T will map a line in V to a line in W. So that kind of makes sense. We saw that a linear transformation preserves linear combinations. It turns out that that extends to preserving lines. A line in V would be a line in W, usually, except in the special case where that line kind of gets squished into a point. All right, so let's prove it. So for this first one, real straightforward. Let's take any vector in our domain V. Then I want to show that the transformation of the zero vector in my domain is equal to the zero vector in my codomain. So all I'm going to do is I'm going to say, well, T of 0, well, the zero vector is just the vector V I chose minus itself. All right? That's a property of vector spaces. I could take a vector and I could subtract the same vector and I get the zero vector. Okay? But now I'm going to apply the properties of linear transformations. The transformation of V minus V is the same as the transformation of V minus the transformation of V. And now I'm subtracting two of the same thing. So something minus itself is just the zero vector. And now that proves the theorem. The transformation of the zero vector is the zero vector. Okay. This, by the way, it seems very simple, but if you're trying to determine if a transformation is a linear transformation, this is a great place to start. Okay. Because if you take the transformation of the zero vector and you get something that's not the zero vector, then right away you can conclude that the transformation is not linear. If, on the other hand, you take the transformation of the zero vector and it is the zero vector, well, then the transformation may be linear or it may not be, but you can't rule it out right away. Okay? But it's a great place to start because it's usually easy to do. And if it fails, you're done. If the transformation of the zero vector is anything other than the zero vector, then immediately you know the transformation is not linear. All right? So now part B. If T is a linear transformation, then T maps any line in the domain to a line, or in certain situations a point, in the codomain. All right? So first I need a line in the domain. So consider the line, or let's say consider the function. X of t, which is equal to v1 plus t v2 where v1 and v2 are in the domain V. Okay? Now remember that generally this is how we express a line in vector form in any specific vector space. We have a point on the line plus t times a direction vector. Okay? then x of t is a line in V so long as our direction vector is not the zero vector. Okay? If the direction vector is the zero vector, this would just go away and we would just have a single vector or a point, right? The vector would point to a specific point. So as long as that second vector is not the zero vector, we have a line in V. All right. Now what we want to do is we want to take the transformation of that line and see if the result is still a line. So next, we calculate the transformation on function x of t. So that's going to be the transformation of vector v1 plus tv2. And now we're going to apply those properties of transformations. Transformation, we can split things up over addition, and then we could pull any scalar multiples out. So I'm going to just apply both at once. So tv1 plus my scalar t I'm going to pull out of the transformation times tv2. Okay. Notice that t of xt, in most cases, this will be a line. A vector plus t times another vector. We have a point on the line. We have a direction vector. This is the general way we express a line. But now we are in vector space W. Note t of xt, which equals tv1 plus my scalar t times the transformation of vector v2 is a line in the codomain W so long as the transformation of v2 is not the zero vector. So same thing that we saw up here. If the direction vector is the zero vector, the zero vector isn't actually pointing anywhere, right? And so this term would entirely go away and we just have a vector that points to a specific point. So we're just getting a point. Same thing here. If the transformation of v2 is the zero vector, well then our direction vector isn't actually pointing anywhere and this whole term goes away. And so then in that case, we would just have a point on the line. So if tv2 is the zero vector, then t of x of t is just a point in W. All right? And so that proves the theorem. And that shows that the transformation of the zero vector is just the zero vector if t is a linear transformation, and that t maps, in most cases, it maps a line in the domain to a line in the codomain. But in rare situations, if the transformation squishes things in just the right way, it might map a line in V to a point in W.